Hello everyone, Namaste. It's me, Javindra Pode. Welcome to my YouTube channel. Today in this video, we are going to learn about the concept of repair, restoration, and retrofitting techniques after the observation of damage to the building by the earthquakes or any other natural calamities. So let me start with the introduction. Repair is the process to rectify the observed minor defect in order to maintain the aesthetical view of the building, and it's not related to strength. It doesn't enhance the strength of the structure. Some minor cracks in the plasters, reinstatement or repairing of doors and windows, tiles, and some periodic maintenance that can be done, and recoloring works as well as any redecoration works, they fall in the category of repair works. And restoration is the technique to restore the lost strength of the structural elements of the building. The lost strength of the building can be restored by the removal of crack portion of masonry walls and piers and rebuild them, addition of chicken wire mesh in the place of cracks or in the walls, and the crack stitching in the junction or in the connection or in the lintel and sill level of doors and windows, injecting chemical slurry to the structural elements such as beams, columns, where there is some voids seen in the structure. It also applies in the slab also. So it is related to the strength. It means with the help of with the restoration technique, the original strength of the structure is regained, but not enhance the strength. In repair, the strength is not achieved. The repair is to maintain the building in aesthetic purpose, whereas in restoration to regain the original strength. But if we look into the retrofit, it is the process to enhance the original seismic load capacity of the structure, which can increase the ultimate load carrying capacity of the structure as well as the ductility or deformation capacity of the structural elements. There are two types of retrofit scheme we will discuss later. So if we look into this figure, this is the typical force displacement curve of the building, which is also called capacity of the building, or this curve represents the pushover capacity of the building. This curve can be obtained by uh, applying the lateral load in the form of displacement and push the structure up to that target displacement limit, and the curve is generated in which the S is the lateral force applied to the structure or seismic base here, and delta is the displacement. So if we look in the black pushover curve, this indicates the capacity of the original structure, and if we do the restoration process, the original capacity, lateral load carrying capacity of the structure is maintained with this. But if the structure is damaged, we can see the curve, red curve indicated by the red curve, and the repair techniques cannot enhance the load carrying capacity of the structure, which is indicated by the green curve. But after the retrofitting, we can see this curve. It can retrofitting enhance the lateral load carrying capacity of the structure as well as the deformation capacity of the structural element. So in the context of Nepal, after the Gorkha earthquake in 2015, most of the structure that were built prior to the earthquake, they are in the process of retrofitting. Many public buildings, office buildings, school buildings, hospitals, and other private housing also, they are in the phase of retrofitting stage. Many of the projects have been completed, and retrofitting is the technique in which, when the existing building is incapable of withstanding the earthquake force, it required to be re-strengthened for safety. So the complete replacement of such building in given area may not be possible due to the historical importance or due to the financial problems. In that case, seismic strengthening of existing damaged or undamaged building is the definite requirement, and it can be fully justified from the cost point of view. In the context of Nepal, if the construction cost, if the retrofitting cost of the building is less than 40% as compared to the original construction, then it is viable for the retrofitting, and it can be preferred for retrofitting. But if the cost exceeds 40% of the original or new construction cost, then the building is better to demolish and construct a new building. So retrofitting is done to enhance the original strength of the to the current requirement. Its current requirement means the seismic code, for example, in case of Nepal, has been updated in 2020, which is NBC 1052020, and the retrofitting is done to make the building compliance as for the updated or latest seismic code or NVC 1052020 in the context of Nepal, so that the current codes of practice can withstand the future possible earthquakes. There are two types of retrofitting techniques. The first one is the global retrofit, and the second one is the local retrofit. Global retrofit involves the global modification to the structural system applied when the structural lateral loads resistance system is deemed to be deficient, and it's a common approach to increase the stiffness and strength of the structure with limited ductility. Addition of shear wall, infill wall, bracing, wing wall or buttress, thickening of wall or increasing the thickness of the existing wall, mass reduction of the structure. It means if we have the building of 5-story and it is not earthquake resistant building as per the current seismic code, then one option is to reduce the floor. We can analyze the building, and for that case, how many floors have to be reduced, we can find out, and the floor can be reduced so that the dead load of the structure can be reduced, and that can also be the way to retrofit the structure. I mean, the reduction of mass is a way itself, a way to make a building earthquake resistance. And another one is the supplemental damping or base isolation. It's very new term in the context of Nepal. In Japan and in other developed countries, these systems are more practiced in real structure also, but in the context of Nepal, it is quite new, and it's in the starting phase. Some building projects in Kathmandu Valley, they are applying the damping technologies. For example, the Hilton Hotel Kathmandu, they have viscous damper. We'll see in further slides. And in another apartment, maybe somewhere around Narayan Gopal Chowk, I think that's Karma Residency. They are applying a wall damper to reduce the global seismic response of the structure. And in the category of local retrofitting, jacketing of beams, jacketing of columns, which consist of steel as well as RCC, beam column junction, and strengthening of individual footing falls in the category of local retrofitting. And these techniques are more popular in our country, and most of the cases in most of the buildings, these member retrofitting or local retrofitting are applied in the present scenario with the addition of along with the addition of shear wall, infill wall, and this damping technology. So if we look into the philosophy of retrofitting, this one is the capacity of the structure. It is strength and drift in y-axis and x-axis. Suppose this is the drift demand of the original structure. After global retrofitting or system strengthening, the ultimate load carrying capacity as well as the drift of the structure has been improved. Whereas in local retrofitting, the drift capacity has been increased, but the global or ultimate load carrying capacity is not significantly increased. If we see this figure, it can be clearly visible here. So this is the example of global retrofitting, which is the addition of shear wall. The addition of shear wall had to be done from the foundation level. In this figure, we see here the strengthening of column from the foundation or footing level with the addition of shear wall. We can see the rebar placing. So it is a most popular techniques in the retrofitting procedure. It greatly improves the lateral load carrying capacity and stiffness of the structure. Existing partition walls are removed. If there are any masonry walls, they have to be removed, and the RC shear walls are built from the foundation level. And these RC shear wall strengthening technique, they preferred the exterior part of the building in a balanced way in both X and Y direction to avoid internal modeling, and thus to balance the mass participation ratio in both directions. The shear wall can resist the majority of the earthquake loads and limit the displacement behavior of the building. This photo of the retrofitting techniques is of Sri Jalpa Secondary School, Kathmandu, where the addition of shear wall also has been done with the RC column jacketing and beam jacketing of the structure. It is a 5-story building, and it is retrofitted to comply with the current seismic code or NVC 105-2020. This is the photo after the laying of reinforcement bar for the column jacketing, shear wall, and the foundation of the column and the shear wall. And these are also some photographs for the addition of shear wall. For doing the shear wall or addition of shear wall, excessive destruction at each floor level result in functional disability of the buildings at the time of construction. If we have to construct, you see this photo here, for the addition of shear wall, we have to excavate the entire area which is covered. Here, this entire area has been disturbed so that any other usage of building in the case in the time during the time of retrofitting is not possible. So this is the photo after the concreting of some portion of the shear wall from the footing, as this is the beam, and the concreting can be done on a step-by-step basis. If the concreting is done from this level to this top or the beam soffit, there may be a chances of becoming the void or honeycomb in the structure. So with the addition of shear wall, the shear wall is concentrated in few places. It is not possible to include the shear wall in whole part of the building, and it's not practical also. It increases the dead load of the structure and overturning moment at the foundation, so that the strengthening of foundation is necessary, as well with the addition of the shear wall. We see here, after the addition of shear wall, there is a huge footing. It's seen here, the river layer of 2 layer, maybe the footing is around 500 mm depth, and it demands, due to the dead load, addition of dead load in the structure, it demands the strengthening of existing foundation, or if there is no any foundation, we have to construct the new foundation for the shear wall in case of retrofitting work. This building is functional after the completion of retrofitting works. The previous photos we have seen regarding to the addition of shear wall, column jacketing, they are taken from this building, and after the completion of the work, the school is handed over to SMC, and now it's in fully operation phase. Another technique of global retrofitting is the addition of infill wall. It's economical method as compared to the shear wall for improving the strength and reducing the drift of the existing structure. And relatively strong masonry wall results in a failure of the column. So proper selection of infill masonry walls should be done in order to prevent the premature separation from the columns. And another issue for adding the shear wall is the anchorage of masonry wall to the frame is a critical factor for overall response. And it should be possible to force failure in the masonry and prevent a premature shear or flexure column failure. So while doing analysis in the building as well, for the new building also, the stiffness of the infill masonry wall is not considered, but only the mass is considered, so that the analysis cannot be done in a real way, or how the wall behaves, infill wall behaves with the addition of along with the columns. But in reality, while constructing a building, there is obviously The partition wall are infill brick masonry walls in superstructure. So we have to look for the combined behavior, or we have to look the behavior of the building with the inclusion of this infill masonry wall. But these things is not being done nowadays in practice while doing analysis or while doing linear analysis for the case of small buildings or low-rise buildings, or in case of high-rise building also, because the interconnection of the masonry wall to the column or to the frame is very complex, and without a proper connection, or the wall behavior of the wall affect the actual response, or another shear or flexure response of the columns. It alters the response of the structure. So it should be we should be very careful while adding this masonry wall as a global retrofit scheme. And in my experience, this addition of infill masonry wall is not preferred so much in the context of Nepal while doing any retrofit scheme. Another global retrofitting techniques is bracing. It's a very new technology in the context of Nepal, and it's more applied in Japan as well. The lateral load is primarily resisted by the axial force in the brace. These braces carry the very high axial force. Columns and beams in the brace zones. The frame away from the brace zone does not have significant moments. It means all the force, all the axial force, it has been carried by these braces, and the column adjacent to brace or beam adjacent to brace, they have very negligible moments. And bracing does not have to be provided in every way, but should be provided in every story. Before providing or before doing any decision where to provide the braces, first of all, the structure has to be analyzed, and the critical portion of the structure have to be found, and after that, the bracing have to be provided in the critical zone. Not much number in one floor, but to be located in the critical zone up to the floor where there is a critical. Now, buckling restraint braces, they can be used to increase the stiffness of the structure by providing energy dissipation and introducing good nonlinear behavior. In the bracing technology nowadays, BRV is very famous because it has good energy dissipation and introducing the nonlinear behavior. Simple braces withstand compression only, but BRV resists the compression as well as tension force. So it is being used widely in the structure for the purpose of global retrofitting, or the structure to reduce the response of the global response of the building. And with the inclusion of these, introducing this type of technologies, the overall response of the building is reduced, and the building can be optimized. The sections of the building can be optimized, because in real performance during the earthquake, most of the energy can be absorbed by this bracing. And simply after introducing this bracing or any other supplementary damping device or any other techniques that can dissipate large amount of energy, or that can absorb the large amount of energy, the structural members like beam columns, they can be designed only to the gravity load, because all the lateral loads can be resisted by this type of technologies, this type of elements. So the frame element, they have to be designed for only gravity loads, by which the structure can be economized, and the overall performance of the structure can also be enhanced or improved. Here, another global retrofitting techniques is supplemental damping. If we see this photo here, these are the dampers provided in each floor of the building where there is a critical zone. As we have already explained, this photo is taken from the Hilton Hotel Kathmandu. These dampers are the first dampers. They are incorporated, or they are applied in the building in Nepal. They are the first damper, and after this, other projects have also introduced this type of damper or wall damper. So this damping system improves the seismic performance of the building, and they are very simple to install. Unlike the conventional seismic retrofitting procedure, using those dampers do not require any significant demolition and replacement of existing element. Therefore, occupancy and building operation are not significantly interrupted during the entire process of installing these type of damping systems. The most commonly used approach in these systems are viscous damper. You see here, or viscoelastic damper, frictional damper, tune mass damper, hysteretic dampers, and wall damper, etc. Friction dampers are one of the type of displacement-dependent passive damping device developed to efficiently dissipate the seismic input energy that can be exerted on the structure. Because the friction damping device require lower cost and less maintenance effort compared to other damping devices, they have been widely used in global are widely used in most of the countries, and also in the context of Nepal, they are also introduced uh, recently for the seismic retrofit of existing building. Finally, another global retrofitting techniques is the base isolation, in which the base isolation technology placing the flexible isolation system made of rubber bearing between the foundation and the superstructure, so that the response of the superstructure can be reduced, and the drift demand of the structure is reduced in significant way. So this rubber bearing consists of a laminated layer. We see here, this is a rubber. This black color is a rubber. It has a laminated layer of rubber and steel plates strongly bound together to design a vertical stiffness design with a infinity vertical stiffness, 300 to 1000 times higher than the horizontal stiffness. And the vertical stiffness is very high, and it causes the natural period of the structure to increase, and the result in decreased displacement across the isolation level and reduce acceleration and displacement in the superstructure during the earthquake. By means of their flexibility and high energy absorption capacity, this isolation system reflect and absorb the part of earthquake input energy, and it's fully transmitted this before transmitted to the superstructure, reducing the energy dissipation demand of the superstructure. It means they are very good energy dissipating devices, and they with the help of the hysteresis loop on the cyclic load that occurs during the earthquake, they have a good broad hysteresis loop. And in analytical case, the area of the hysteresis loop in its cycle is the amount of energy dissipated by this device or absorbed by this type of devices. So this is the simple base isolation structure in which there is a lead core, the elastomeric high damping rubber, and these are the flanges. These are the retrofitting steel discs with a rubber cover. The rubber and the discs are uh, inserted with a layer by layer basis, and they are strongly bound together. And these two holes in these above plates and the base plate is to tie this bearing on the RCC surface. Suppose if this bearing is placed on the foundation level, on the plinth level, the structure below the plinth level is tied on this plate, and the structure above the plinth level is tied on this plate. And the entire energy dissipation of the imposed by the earthquake is absorbed by this mechanism. I want to stop the today's class here. In another class, we will continue from here. In that class, we will learn about local retrofitting schemes and some challenges while doing retrofitting schemes. Until then, keep watching my videos. Don't forget to like, comment, and subscribe my YouTube channel named Chavindra Paudel to get more information about structural engineering, retrofitting of structure, and other civil engineering related content. Thank you.